Hello, in this unit we'll be covering polar coordinates. A lot of what you do here isn't really technically helpful, but it helps you get the grasp of polar coordinates. It's really supposed to be a good foundation for understanding them. Because in the next calculus, Calc 3, multivariable, you're going to have to be using what's called cylindrical coordinates, and that's going to heavily rely on polar coordinates in order for you to be able to use them. And they'll also be used heavily in a lot of other different things. It just makes finding areas so much easier for a lot of different types of graphs you may have. And it's just going to be learning this is really just about using it for other things. You're not going to be trying to find all the different um, intersecting points along a pathway. You're not going to be doing a whole lot of this, but it's really about understanding how this works, and like how we use polar coordinates and how it relates to x, y, or spherical. And we're going to be, it's again, like I said, it's a foundation. So we're going to go ahead and get started. We're given the equation r equals 1 over 4 plus 4 sine theta of a conic section with one focus at the pole, and find the equation of the corresponding directrix. So we know focus is at the pole meaning the origin. This is where the focus is, F, 0, 0. So we need to find the equation of the corresponding directrix. So we know that we should rewrite R to equal 1/4 over 1 plus sine theta, which we know is equal to KE over 1 plus sine theta. Or sorry, 1 plus E sine theta. So we know that E has to equal 1 because that is the coefficient here in front of the sine. And so if that is 1, that means that K by abduction is going to be equal to 1/4 or process of elimination, whichever method you like to call it. So then that means that your directrix is going to be equal to y equal to 1/4. Because again, our focus is at 0, 0. All right, if the focus was at a different pole, it would shift our directrix up or down. If the focus were up or down, but since it's at the pole, it's going to be 2K away. Now it says sketch and label the directrix found in A. All right, okay, we already did that. That's the directrix. Its corresponding focus and the vector, is that what the heck is it? Oh, vertex, I'm sorry, I just blanked really hard. And vertex. So we know that, again, it's going to end up being, your vertex is going to be half the distance from your focus or from your directrix. So it's going to be that entire distance from your focus to directrix. So that's K. I misspoke earlier. I said 2K earlier, but it's just K. And then your distance from your focus to your vertex is going to be half K. So this is going to be 1/8 here. And again, we have to write this in terms of polar coordinates. So 1/8 is your magnitude R, and the angle is going to be pi over 4. So that's R theta. And if you want, I don't think it'd be wrong. I think you could write it as 0 1/8. You just have to make note of what variable or what reference thing are you using, what coordinate system are you using. Oh, its corresponding focus. Oh, you have to circle these things. And vertex, wait a second, the conic section is is going to be a vertical parabola. All right, so know this equation. K just represents the distance from here to here. Or is that KE represents a distance? I think it's just K. We should look at the review. Don't want to be wrong. Directrix perpendicular to polar axis, x equals negative p. Okay. And polar axis, x equals p. Okay, so it's going to be whatever your k is, or wherever your rho is, or p, wherever you want to call it, wherever that value is. That's going to be your distance. Eccentricity just decides what it's going to be. If it's 1, it's parabola. Less than 1, it's ellipse. Greater than 1, hyperbola. So make sure you go over this content because they may ask more than just a parabola. All right, so now, wait a second. Actually, is this the equation sheet they gave you? Okay, you'll be given this equation sheet. Okay, that's right. I forgot to give this to you. They'll give this to you, so don't worry about it. Sorry, I jumped the gun on that. But again, this tells you everything you need to know. So just know how to use this equation sheet and what everything means. So yeah, y equals k, and your distance from the focus will be k, as long as your focus is at the origin or say pole. All right. So yeah. All right, so next we have graph the set of points defined by r is greater than -2, theta equals -pi/4. So I always think of it, we need to look at r. So we know r is going to be greater than -2. So it's going to be going in the opposite direction of whatever our theta is in. To begin with. So because we know we're going to start at -2 and then go backwards, it's going to constantly increase. Not backwards, it'll just constantly increase. So our theta is -pi/4. So again, this is 0, pi/2, -pi/2. So we know we're going to be in this direction. So we know we're in that direction, and we know that -2 we'll say is right here. Because again, we have to go in the opposite direction of the pole if it's a negative radius. So this is -2 pi/4. Sorry, -2 pi/4. And this is just at theta equal -pi/4. You don't need to write all of that. You can just draw just a line. But it's really helpful if you draw what you think everything is. Yeah. So that was just essentially a ray, kind of like a line, but with the endpoint. Now we have a radius from -1 to 2. So we have a range for our r, but we also have a range for theta. So theta just has to be less than pi/4 on the absolute scale, which means that theta can be greater than pi/4, or theta can be greater than -pi/4. Or we can write it like this. Because we have a positive and negative case. So we already know what -pi/4 looks like right here. Positive pi/4 is right here. So that's our range for our theta. And then I'll go ahead and label this theta equals pi/4. Oh, I don't know what I'm doing. Pi/4. This here theta equals negative pi over 4. And we're going to be all inside this range. But our range, or for our radius, is from -1 to 2. So we're going to call this radius right here 2. And I'm coloring this in because this includes all of this. And now we have from we have -1. So we know when we're at r equal to 2, or we're at, sorry, theta equals pi over 4. This is r up to 2. And then all the way, got to go in the opposite direction to -1. Same deal for negative pi over 4, -1. Draw your radius there. So this is r equal to -1. All right. So not too bad. Next one, we have to convert our xy coordinate into polar, with r being less than or equal to 0. So you have to have a negative r. And theta has to be between 0 and 2 pi. So r having to be negative, we know that r has to equal negative square root of your x squared component plus your y squared component. So that's going to be negative 2 square root 3 squared plus -2 squared. And so that will equal 12 plus 4, 16. So square root of 16 is 4. But it'll be -4. Because again, we're taking the negative root because we want a negative radius. And then we need to find our theta. So our theta is going to be dependent upon our x and y. So we have to look at cosine theta, which equals x over r. So it would be square root 3. And because I did, here, I'll do like this, -2/3 over -4. So I'll get, oh, see, I messed up anyways. So we got square root 3 over 2. And then we'll do sine theta, which is y over r, which is -2 over square root of 3. Oh, -2 over -4. My bad. Which equals 1/2. And we know that angle is going to be theta equal to pi over 6. Because again, that's where you have your y equal to 1/2 and your cosine and your x equal to square root of 3 over 2. And this makes sense because if this is our point on the graph here, it's about there. And we have theta pi over 6 and a negative r of -4. So now we're here, now we're going backwards, -4. So that makes sense. We need an angle in the positive quadrant to get with a negative radius to get into the negative quadrant, from the first quadrant to the third quadrant. So then this means you'll have -4 pi over 6 r comma theta. All right. So this next one, we have convert to Cartesian coordinates and sketch. Show your work. All right, so tangent theta, we know the relation there can be sine and cosine. So I'll say sine theta over cosine theta equals 1. But then I can also put r's here. And then now this becomes y x. So then we have y equals x. And then means we have a straight line of y equal to x. And the only time where y equals x is at theta equal to pi over 4. So that kind of makes sense. If you find tangent inverse of 1 equals theta, it would equal pi over 4. So that makes sense. So the next one is a little bit more work, but not too bad. So we have r equals cosine theta, cosecant squared theta. Go ahead and get this all in terms of sines and cosines. So I'll multiply that cosecant squared over, or well, I'm going to divide by it, which means I'm going to have sine squared over here. So we'll have r sine squared theta equals cosine theta. So that means I have r squared. Oh, and so I'm going to multiply by r on both sides. So that way I can get a r sine, and r cosine. So I have r squared sine theta equals r cosine theta, which means this now becomes y squared equals x. And that's going to be a parabola that's opening in the positive x direction. It's horizontal. All right. Yeah, it's pretty much getting into that x equals r cosine and y equals r sine stuff. And doing whatever you need to do that. Okay, so now we have find the value for theta naught and r equal to 0, where theta naught is between 0 and 2 pi. And they gave us all these relations here. So let's find the values of the slope dy dx at the pole. So to get so let's find the values for theta naught where r equals 0. We set r equal to 0 for that first equation. Which equals 1 plus 2 cosine theta. We're going to call it theta naught. Which means theta naught is going to equal cosine inverse of negative 1/2. So that means we're going to either be in the second quadrant or in the third quadrant, because that's where x is negative. So we can say it's going to be either 2 pi over 3 or 4 pi over 3. So it can be both of these. This is theta naught. All right, so now we know our angles. Now I need to find the value of the slope dy dx at the pole. So he gave us this tangent theta naught, comma r. Oh, what the heck does that even say? Gx. Okay, kind of. Okay. All right. Oh, okay. This is saying dy dx is equal to those things. Okay. So we don't know r prime, so we can't really solve for that. Or I guess we could. We could solve for r prime and plug it in, or we can just plug in to this where he says. I think this means is that. Actually, I'm confused what this symbol here is. We can use it. I just don't know what that symbol is. R equals 0. I think it means at the pole. Oh, that's an at. Okay, yeah. All right, so we can do this. So dy dx equals tangent theta naught when our r equals 0 at theta naught, which it does. All right, so we're good. So we can then say tangent theta naught, which is 2 pi over 3, equal to and we can either figure it out from there, or we can do it in terms of sines and cosines. Either way, we'll get negative root 3. So this is slope, and we have to be careful. This is slope 1, so I want to call this M1. Because again, we have two different cases. They have M2, which is going to be whenever tangent theta naught is going to be 4 pi over 3. And this is going to equal positive square root of 3. That's all you have to do. If you need to use the other equations, because again, it says at the pole. If it didn't say at the pole, then that means we couldn't use the tangent theta. If it said anywhere else, if they said at theta equal to whatever, at r equal to whatever, that isn't 0 or theta at the pole, then you couldn't do it. Then you have to use these other two equations. Or the other equation, not other two equations. That's all one equation. All right, because that's pretty much the chain rule there. All right, so that's everything you need to know for here. All right, next page. So then we have r equal to 1 plus cosine theta. It says refer to 10. Okay, refer to 10 for dy dx. So once dr d theta. So dr d theta is not the same as dy dx. So we have to just take the derivative here, which is going to end up being negative 2 sine theta. And I'm assuming d theta is considered a constant. Yeah. Or it's not varying with any other variable. Yeah, we can do that. So now it says find the slope at theta equals pi over 4. So that means we need to plug this in to our dy dx, which is equal to prime. So it's going to be this negative 2 sine theta. Screw up a little more. Plus sine theta. I think I said r again. But sorry, I said r. So it's going to be 1 plus 2 cosine theta. I'm glad they picked pi over 4, so it'll be the same value for all of these. Cosine theta all over. Yeah, keep I'm cosine theta, so negative 2 sine theta cosine theta minus, I think it's r sine theta. 1 plus 2 cosine theta cosine or sine theta. So we know theta is going to equal pi over 4. So that means each of these is going to become square root 2 over 2. Or I think it might be easier if it's 1 over square root 2. It's the same thing. All right, so then I can plug this in as, this would be negative 2 over root 2 squared, which is just 2, plus 1 plus 2 root 2 times root 2, 1 over root 2. All over, this is negative 2 over 2 minus 1 plus 2 over root 2, 1 over root 2. So we're going to end up getting, this will be negative 1. Here, I'll do this over here. Negative 1. When I distribute this, this becomes 1 over root 2. This becomes 1, so these will cancel. We'll have negative 1 here. This will become minus 1 as well. This will be minus root 2. Minus 1 over root 2. So we'll get 1 over root 2 all over negative 2. That's going to be minus 1 over root 2. And we can simplify this just as negative 1 over 1 plus 2 root 2. So either of these are fine. All right. Again, this is just plugging and checking with the equations they give you. So given r equals 1 plus 2 cosine theta, find alternate equations show work. So for this, you have to rely on the this equation, r equal to -1 in f of theta plus n pi. So for the first one, we'll have r equal to, so for all of these, this r will equal to -1 to the n times 1 plus 2 cosine theta plus pi, n pi. All right. So we know for n equals 1, we'll have r equal to -1 times 1 plus 2 cosine theta plus pi. Which will equal -1 minus 2. And we'll go ahead and use the identity for cosine theta, cosine pi. So this goes to -1. And it's plus, so it becomes minus. Sine theta, sine pi. This goes to 0. So all this goes to 0. Then we're just left with -1 plus 2 cosine theta as an equivalent equation. And then n equals 2, r will equal +1, because it'd be squared, times 1 plus 2 cosine theta plus 2 pi. So it equals 1 plus 2 times cosine theta, cosine 2 pi. This is just 1. Minus, it'll be the same deal here. It'll be 0. And we're left back with the original equation, 1 plus 2 cosine theta. So remember, these equations have the same pathway, but they don't necessarily have the same starting point or at the same point at the same time. They will just, like, if you were to plug this into an equation on your calculator, it'll look exactly the same. But where they start or where they're at every single point with respect to theta will be different. So that's the one thing to make note of. All right, so now we have our equations. Now we need to test for symmetry with respect to all of our different things. So if it's symmetric with the pole, that means you were able to replace r with -r and have the same equation. So in this case, we're only doing this with the original equation. We're not doing it with all of them because, again, there's alternate equations. We'll have -r equal 1 plus 2 cosine theta, which means r is equal to -1 minus 2 cosine theta. If this happened to equal our alternate equation or the original equation, then it would be symmetric. But since it's not, then it doesn't work. So no, not symmetric with respect to. And then we have x-axis. So for x-axis, we have to replace theta with negative theta. So we have r equal to 1 plus 2 cosine negative theta. And we have to know our identity for cosine theta and cosine negative theta. Cosine's an even function, so we know that f of negative x is going to equal f of x. So we know that this is going to equal the same equation we had before. So r is going to equal 1 plus 2 cosine theta So yes, it is symmetric since it matches up with this equation here. So it's the same as the alternate equation. Or, sorry, not the alternate equation, the original equation. If y-axis, you have to replace r with negative r and theta with negative theta. So we're going to have negative r, oh here, I'll write it out, r comma theta, replace with negative r, negative theta. So negative r is going to equal 1 plus 2 cosine negative theta, which is just going to equal r equal minus 1 minus 2 cosine theta. Because the negative theta did not change the sign, so no. All right, so given r equal to 1/2, find alternate equations, show work. So we know r equal to 1/2. I mean, this is the same deal as before, and it's kind of annoying, but I don't know why they did this. It's actually a dumb problem. R equal to negative 1 to the n, f of theta plus n pi, which means this is negative 1 to the n. Negative 1 to the n 1/2. Is that it? Yeah. So this is for any theta. So this is for, because again, this is pretty much a circle. So when I plug in for the next r for n equals 1, I'm going to get negative 1 1/2, which is equal to negative 1/2. Then I do for n equals 2, r is going to equal positive 1 times 1/2, so it's 1/2 same, so you stop. Same as original. So stop. So this is now our second, this is our first equation. So we have r1 equal to 1/2, r2 equal to negative 1/2. Yeah, bad writing right now. All right, now we have to prove that r1 is equal to 1 plus 2 cosine theta and r2 is equal to 1/2 do or do not intersect at the pole. All right, so that means that we need to set r1 equal to 0 and r2 equal to 0. R2, or well, sorry, looking at the wrong setting point. Let's see here. Yeah, we have to set r is equal to 0 because at the pole means we have to be at the origin, which means r has to equal 0. So I know when I set r1 equal to 0, it's going to 1 plus 2 cosine theta. It implies theta equals negative, or cosine inverse of negative 1/2, which is going to be equal to plus or minus pi over 3. Sorry, I just want to scroll up for a second. Yeah, that's the same one as earlier. I was just wanted to check. So now we have that, but then for R2, we do not get that. R2 cannot equal, because 1/2, and cannot equal 0. So they do not intersect. At pole. Says find the values of cosine theta, not theta, that you yield collision. So collision is different than intersection. So collision should be at the hit, they're at the exact same theta. So R2 has to equal R1 at the exact same theta. So you have to do it with the original equations. Here, I should probably rewrite this as. So we say 1/2 is equal to 1 plus 2 cosine theta, which implies cosine theta has to equal -1/4. So that is a collision, meaning they're at the same time. So I couldn't use an alternate equation for these things. I could find other intersection points, which I'm going to do in the next one, but they're not the same as collisions. So I have to set these to the other variants. So here, I'll go back on this A1, A2, or wait a second, how should I label this? Here. There we go. Call it A1 for these, or wait, it'd be A2. So R2, A2, and then up here, this is R1, this is R1A, alternate. All right, so I need to set the alternates and other variations equal to each other. So I have R1 equal to R2A, which implies 1 plus 2 cosine theta is equal to -1/2, which implies cosine theta equals -3/4. So that's only if R1, so that's at R1 equal to R2A equal to -1/2. All right, now we have R1A equal to R2. So this will be, what was it? It'd be 1 plus 2 cosine theta. Oh, wait, no. That was the original. Oh, whoops. I messed that up here. I knew what I was writing out, but. All right, so that's A. So we have -1 plus 2 cosine theta is the A. So -1 plus 2 cosine theta is equal to R1, or R2, which is 1/2. So we add 1 to get 3/2, divide by 2, so we get 3/4. So cosine theta would equal 3/4. And that's at R1A equal to R2 equals 1/2. So those are the other intersection points. And I don't think you have to do the alternates equal to each other. Yeah, I don't think you need to do the alternates equal to each other. But we'll go ahead and just show what happens. R1A equals R2A. -1 plus 2 cosine theta equal to -1/2. And then this implies cosine theta equal to 1/4. Yeah. But we don't know an R. Yeah, we do. It's whenever R equals -1/2. Oh, actually, you don't do this. So the reason why I don't do this, I just realized why, is because these are not, being related to one of the original equations. We need to use one of the original equation combinations, not the alternates. Because that's already a point that we have. Because if you want to, because if you do cosine 1/4 at -1/2, we can look, it's the same as this point here. So we didn't need to do that. All right. Okay. Or sorry. Yeah. Don't do the alternates. You don't need to do alternates. That's it for this video. Let's see what kind of pictures on my desktop. Oh, look at that. Look how cute that cat is. That's Ernie. Ernie says good luck. I say good luck.